next page here. So let's take a look at water. Why is water liquid, and what's the difference between solid water and liquid water? H2O is H2O is H2O. So when you have steam water, what you call steam, it's a gas. So just like any other gas, it goes in every direction, fills up the space. There's no definite volume or shape. So that's just steam. But quickly, if there's a lot of steam in the room, quickly it goes right back to liquid. Why does it go back to liquid so easily, where oxygen and carbon dioxide don't? They're sticky. And what's the force, what's the bond that we talk about when we talk about water being sticky? Hydrogen bonds. The hydrogen bonds pull them back together into liquid that quickly. This is a really important property of water. All right, so when we look now at that's steam. Now when we look at a liquid water, again, we have that shape, right? I'm just going to draw this. Kind of a big one, a little one, and the big one's going to attract the little one, right? You should be able to draw this. So you asked me what I expect you to be able to do on a quiz or identify. You should be able to tell me that this is kind of the shape that you'd expect, right? Now, in a liquid form, what the interesting part is that part of what defines, and I think you all know this intuitively, but let's be clear on this. The thing that defines what kind of, whether you have a gas, a liquid, or a solid, is what? There's two things. There's pressure, how much they squeeze them together, and energy. And then the energy we talk about is what? All right, heat, temperature. By the way, temperature is something you should know already, but let's go ahead and look at it. Temperatures is a measurement of average kinetic energy. Do you remember kinetic energy? All right, kinetic energy is the energy of movement. So the higher your temperature, what would you expect is going to be happening? The more moving. Does that make sense to everybody? Yeah. Anybody if you have a problem with it, you don't understand it, please say something now. So the more kinetic energy, the higher the temperature, the higher the kinetic energy, the more moving you have. So gases move the most. They're moving all over the place. They're the highest temperature. Whatever that temperature is. At what temperature does it turn into a gas where it's moving the most? It depends on how much pulling they do to each other. If you have a small non-polar molecule, then it doesn't take that much energy to make it into a gas, make it move far and fast, right? So oxygen and carbon dioxide, they don't pull on each other. A little bit of temperature makes them into a gas. You have to get them real cold. You have to slow them down a lot to get them to turn into a liquid and then a solid, or increase the pressure, squeeze them together. All right, the other thing that you get when you decrease the temperature, you get this liquid water. You go from gas to liquid, condensation, right? But this water, these molecules are moving still, right? Because they're moving more than they do when they're solid. But they're not a gas, so they move around each other. Does that make sense? Yes or no? Thank you. So they squeeze into each other. They do this. They'll squeeze in. And they'll roll. Maybe this one rolls this way, and that one rolls that way. These kind of flow over each other. That's why water flows. This is liquids flow. They move. The molecules are literally rolling over each other. Like imagine a bunch of bingo balls or a bunch of ball bearings, and you pour them out of a jar. How they roll over each other. Well, that's what these molecules are doing. When you're looking at water, you're looking at tiny little molecules all flowing over each other. You got to use your imagination here. But when water becomes a solid, something interesting happens. And it's very interesting and very important. When water becomes a solid, water does this. It forms its shape. It lines up like soldiers in a formation. The positives and negatives line up. Why? What makes them line up this way? And this is going to be the answer to 90% of your questions in biology. When it comes to molecular biology anyways. What is it that makes them line up this way? You know the answer. I wouldn't be asking you. No, temperature allows them to. Yes, it slows them down. It reduces their energy, so they're not moving so much. As soon as they start slowing down, what pulls them together in this fashion, makes them line up this way? Hydrogen bonds. So hydrogen bonds make them line up. Now it turns out that the way they line up when they're a solid, bless you. The way they line up when they're a solid, they're more spaced out. They're more spaced out than they are when they're liquid. Why is that important? That the molecules are more spaced out when they're solid than when they're liquid. These molecules are more spaced out as a solid than they are as a liquid.
That's because
Yeah.
liquid molecules are like moving around and rubbing against each other.
Absolutely. Because they're moving around, they have more energy, they're moving around and swishing and pushing and pulling on each other, that's fine. But now they're calmed down a little bit, slower, lower energy, they're lining up, they're spread out. So now they're spread out. What does that mean? What's the implication of that? So what? 4 molecules of water spread out, 4 molecules of water not as spread out. What does that mean? Yeah. Well, they're attracted to each other equally, but there's more energy here, so they're sliding around each other. Let me go ahead and give you the answer. Yeah. They do have less energy. That's all true. Everything you're saying is true, but it's not the point I'm trying to get at. What is the implication of all that? So here's the implication. Solid water, yes, has less density. So it's less dense. So what does solid water do in liquid water? It floats. Why do ice cubes float? Why do ice cubes float in water? They're less dense. Why are they less dense? Because they've lined up and formed this geometric shape. They spread out. Why do they spread out? Because they're pushing and pulling each other. Why? Because of hydrogen bonds. Hydrogen bonds line them up so that they take up less space as a solid than they do as a liquid. You may not, does anybody know what density means? What does density mean? What does density equal? Density equals what? Good. I heard the word volume is correct. There's something to do with volume. And mass, correct. It's mass divided by volume. So what is mass? Mass is, let's think about it. Mass is how much you have of matter. And what matter are we talking about? What is the matter we're talking about? Water. Water molecules. So in this case, it's how many water molecules you have. Each of those atoms have a mass, right? We talked about that. Each atom has a mass. If this has a mass, and that has a mass, and this has a mass, you can add them together, right? And if you can add this mass together, you can add them all together, right? And you'll get a certain amount of mass. Do you agree? Whatever that mass is. I used to have kids calculate them. We could calculate if you have a periodic table. We could go ahead and add them all together now. Take hydrogen's mass of 1 point something, add it to 1 point something, add it to oxygen's mass, then multiply that times Avogadro's number. We could figure out a lot of stuff. But we're not going to do all that. Here's my question to you. We have this, so when we have this amount of mass, this number of molecules in less space, and by the way, what is volume? What is volume?
How much space is taken up?
That's right. Does everybody understand that? And how much space is the matter taking up? So if I have a mass of 10 grams, and I have it in a box that's 1 centimeter by 1 centimeter by 1 centimeter. And volume in a cube is going to be calculated how? How do you calculate volume in a cube? Length times width times height. So it would be 1 centimeter what? Cubed. Another term for 1 centimeter cubed is cc. You've heard of cc's? Give them three cc's of something in a movie, in cartoons, or in shows on TV. cc is cubic centimeters. 1 cubic centimeter is the same as 1 milliliter. That's what a milliliter is. It's the amount of space taken up by something that's 1 centimeter by 1 centimeter by 1 centimeter. That's it. That's all it is. I know it sounds all kinds of crazy, but it's really just that simple. Is this amount of space inside this cube, right? This amount of space is 1 milliliter or 1 centimeter. That's it. That's all there is to it. If you have 1,000 of these, what do you got? Which is what? 1 liter. So 1 liter is 1,000 milliliters. So you take 1,000 of these little cubes, put them together, that space that takes up is 1 liter. So what's 2,000? 2 liters. Your 2 liter Pepsi, right? It's that 2 liter bottle could hold 2,000 little squares, little cubes. That's all. That's all we're talking about. It's just space. How much room does something take up? That's volume. So how much stuff is there in this cube? If this cube has 10 grams in this cube, but I have another cube that takes up more space but has the same mass, now this cube has the same mass, right? But it takes up more space. Let's say it has 20 grams. No, I'm sorry, that's not right. It still has 10 grams. Same mass, but now it's taking up less space. Now it's 100 centimeters by 10 centimeters. No, let's not do that. I'm trying to make this work out right. But let's just forget about it. Let's say 10 centimeters by 10 centimeters. What is this? What's the volume of this cube? What did someone say? Yeah, obviously I'm drawing it badly, but let's move on. Let's let it go. Sorry. I'm sketching this. It's a sketch. I'm not going to worry about details. You want to pull out the T-square and make a perfect square, go ahead. But if we take 10 centimeters times 100 centimeters times 10 centimeters. But you know what? I jokingly said that, but you're right. Okay? This would not be a square, and so there wouldn't be a cube. So it would be a little off. But can we just go ahead and assume this is a cube? Okay. So what is this? What's the volume here? 10,000. Everybody agree with that? I agree. 10,000 cubic centimeters. Same mass, same number of molecules, in more space. Which one's less dense? Which would you rather pick up? Which one's going to feel heavier? No, they both feel the same weight. They both have the same weight because they're both, what, 10 grams. right? But one's bigger. So which one of these is more likely to float? The big one. The big one. Which is heavier, 1,000 pounds of iron or 1,000 pounds of feather? They're both the same. 1,000 pounds of feathers is exactly the same as 1,000 pounds of iron. What's the difference between the two? One's more dense, so what does that mean? How big, or let me use this something more reasonable. If I have 100 pounds of iron, who lifts weights in here? How much does 100 pounds look, what does 100 pounds look like? It's a bar, maybe a couple barbells, maybe 250s on each, and well, probably two. Let's just go ahead and say 250s, ignore the mass of the, let's say 250 discs about this big, two of them are 100 pounds. That's how much space they're going to take up. About this much height, about this round. Everybody agree? We're going to go with it. If I had 100 pounds of feathers, how much space would that take up?
Like half of this room.
A lot. I don't know how much, but it'd be a lot. I mean, the feathers that are not, assume they're not compacted, they're going to be big, right? Or we could maybe half the room, right? Filled with feathers. So feathers are probably going to float, where the iron probably is not. So why is all this important? I'm going to quickly give you the importance of this, and then we're going to go on. You're going to have to do Cornell notes and write down the important stuff yourself on the lines where appropriate. It's almost time to go, but please write down this last bit. If you have a lake in the wintertime, and you know what the lake looks like in the wintertime, which side, what freezes first? The top freezes because it's the coldest. Now this whole thing's frozen. That means it turns to solid. It's solid. It's floating, isn't it? This acts as an insulator. So now the poor fish that are down here, stop laughing at my fish. All right, I can. The poor little weird mutated fish at the bottom of the lake can live happily in the liquid water down here. It's not going to turn into fish sticks, right? Because it's at the bottom of the lake. Now, what would happen if water didn't freeze? What if the density of water wasn't what it is? What if it did not take up more? What if solid water did not take up less or more space? What if it took up less space? Then, as the ice froze, where would it go? It would freeze from the bottom up. That means everything in the lake would freeze. There would be no life on Earth. There couldn't be life. If all life started in the oceans, then if water froze from the bottom up, then we'd have giant ice cubes every winter. And there's no way for fish to survive that. So the fact that water freezes, the ice floats, and water freezes and floats at the top, this is very important for life on this planet. So the poor little fish, I could draw a better one, but I'm going to erase it because it's embarrassing. All right. Are we all good with this idea? There's more properties of water. We'll finish it tomorrow. Have a good one. I just want to reiterate, when we talk about the properties of water, one of the things about water is that water freezes at the surface, and it floats. Water floats, right? And it floats because it is less dense than the liquid water. So solid water is less dense than liquid water. This is very, very different from most molecules. Most molecules that are like water, as far as their size, they're solid form. Most things, and I think you learned this in middle school, right? I think you know this inherently. Most things, when they are solid, When they're solid, when they're gas, the molecules are very far apart, right? When they're liquid, they're closer together. Do you remember that from middle school? All right. And when they're solid, they're very close together. Is that right? Is that what we learned? That's most matter in the universe is like that, right? Iron is that way. If I had liquid iron and solid iron would sink because solid iron's molecules or atoms are closer together. If I do almost any substance, that's the way it works. Water's really weird. It's not the only one that's like this, but it's one of the few. And water's weird because of what? What is it that makes water weird? What makes it have this less dense solid form? Because of the its sticky nature, that's right, but what specifically what? Yeah. Surface tension is a result of this as well, this thing I'm looking for. I think I labeled it. Didn't I label it already? Or is it let me hold it. Let me pause this. So I just want to make sure that I covered it, and I did. I just went back in notes and looked at it. You all saw it. You should have it written down. Water is weird because it has hydrogen bonds. And what do we mean by hydrogen bonds? We mean that there's either fluorine, nitrogen, or oxygen, right, bonded to a hydrogen. So in the case of water, it's what? It's oxygen, right? It's this one. And that makes this negative and this positive, which makes the molecules of water line up in a way that spreads them out. It spreads them out. So it makes them less dense. It makes them take up more space than they would than the liquid form. Liquid, they have enough energy where they're all rolling around each other. They break those hydrogen bonds. Now this is not a hydrogen bond. Let's make sure we understand that. This polar bond is what causes hydrogen bonding. So if there's another, instead of this, because this is negative and this is positive, because this is positive, that hydrogen bonding is happening. This is the hydrogen bond. It's the bond between the molecules, not the bonds that hold the molecule together. Okay? This hydrogen bond is weak. This is a weak bond. But it's strong enough, if the energy's low, if it's really cold. How cold? For water, 0 degrees Celsius at 1 atmospheric pressure, right? So at 0 degrees Celsius, this bond becomes strong enough to make it all the molecules line up and spread out. That's what makes snowflakes in part, right? Snowflakes are formed because of this. Ice floats because of this. This is very important. Again, if ice floats, then it can act as an insulator in the wintertime. And that allows water to freeze without everything underneath it. All the living things in the lakes or the oceans die. Right? If you go to Antarctica, it's extremely cold out on the surface of Antarctica, and if all the ocean's frozen, that part of the ocean's frozen, underneath that ice, at the bottom of the ocean, there are things that are alive. They move real slow, but they're alive down there. And that's because that ice acts as an insulator. That very thick ice acts like a blanket, and it keeps this water from freezing. All right, so that's an important aspect of water. Important property of water is that it is less dense as a solid than as a liquid. Okay? That takes care of water, takes care of density. Let's go on.